Hello, hello. Welcome to Learning Haskell. So I'm although this channel is about NixOS and all the Nix stuff, I love Haskell. And I love Haskell. Yeah, I've been learning it proudly since 2016, all right, and I still don't know it and I don't program in it. I read a couple of books, but not complete books. I just, like you start to read a book, you get to some point, it becomes, I cannot like maintain everything in my head, and then I drop or I start again to read the book and I reread, and then something in life pops in and then I stop with the book and then I come back to it. So that's kind of the iterative process. Um, I um, I wanted to make a series of like books, going through books, and I bought now the Bird book, thinking functionally with Haskell, and I bought also programming Haskell, and I'm watching the amazing C9 lectures, and that's now on YouTube. Before it was not on YouTube. Dr. Eric Mayer, the functional programming fundamentals. These are really great. I really recommend this. But what I want to do, and I want to type like, and I just don't want to read because a lot of the Haskell books are about like unpacking the meanings and reading about what is a function, what is really a function, and then you advance and then you really start to ponder what is a function, what is this and what is that, and you kind of, there's so many words. And me coming, having a background in guitar, like I play and improvise and I do music and sound. So one of the like important things is to really play with the instrument, play with the sounds, and not just read about them. So I actually, I wanted to do a stream from about the Haskell programming from first principles. That's the other book that I bought in 2016. And also a type of programming. This is another great book from Renzo Carbonara. But now I'd like to start, and this would be more like a yoga kind of a thing. Like I want to learn you a Haskell for great good. I think I'm ready now to really do this book. Now there is a site, Learn You a Haskell for Great Good, and I remember the site was down. But if you Google Learn You a Haskell, you can find Learn You a Haskell for Great Good up to date, which may be an up to date version, an up to date community maintained a version of the renowned Learn You a Haskell guide for Haskell, packed with artwork, pop culture references, right? Let's do that. Buy it, you know you want to. Read it online. I can read it online for free, right? Learn You a Haskell for great good. I like this because it's a lot of typing and playing around with it, right? So I think I'm ready now for this book. I'm ready. Introduction. All right. Introduction. We have our we don't have. Let's go to console. Let's go to console and let's go to cd dev Haskell. Haskell, as Graham Hutton says. Let's make a directory. Learn you, learn, learn why Haskell, learn why Haskell. Just learn you a Haskell. LYH. Let's call it LYH. CD LYH. And let's just start. Introduction, right? GACI. I'm on NixOS. This is GHCI version 9.6. I'm on NixOS. Yeah. Let's make this really big because it's fun. I don't have anything special installed, just the GAC and ball and just the basic ones. I just declared them in configuration.nix. So I don't have kind of a special template kind of a thing because that's a really thing with Haskell toolchain. Sometimes like you're not even sure how to install it. Okay, let's just start. Welcome to Learn You a Haskell for Great Good. If you're reading these, chances are you want to learn Haskell. I do. Well, you've come to the right place, but let's talk about this tutorial a bit first. I decided to write this because I wanted to solidify my own knowledge of Haskell, and because I thought I could help people new to Haskell learn it from my perspective. There are quite a few tutorials on Haskell floating around on the internet. When I was starting out in Haskell, I didn't learn from just one resource. Yeah, right. You learn from like 1,000 resources and then you still don't know. The way I learned it was by reading several different tutorials, right? And articles, right? Because each explains something in a different way than the other did. Like the monads, right? By going through several resources, I was able to put together the pieces and it all just came falling into place. So this is an attempt at adding another useful resource for learning Haskell so you have a bigger chance of finding one you like. This tutorial is aimed at people who have experience in imperative programming languages. Not much. C, C++, Java, and Python. Actually, Haskell was my first language, my real first. And yeah, I just love it. I love it that I don't have a background in imperative programming, which kind of makes me incapable of doing anything. Okay, but having programmed in a functional language before, like Haskell, ML, or Camel, although I bet that even if you don't have any significant programming experience, a smart person such as yourself will be able to follow along and learn Haskell. All right, the channel Haskell on Libera Chat. I don't know if this still works, but there is a nice channel on Matrix and on Slack. I remember the Haskell programming for beginners or something. There are stuff like if you go to Haskell, the wonderful Haskell.org, probably, right? It should be a website, Haskell.org. There's Haskell.org and advanced. We are advanced. The community. Look, there's so much here. There's a lot of stuff now. Yeah, right. All right. People there are extremely nice, patient, and understanding to newbies. Right. I failed to learn Haskell approximately 2 times. I've been failing to learn it for like 8 years. All right. Yeah, that's not so bad. 2 times before finally grasping it. Oh my God, that's some what's it called? Hubris. Finally grasping it because it all just seemed too weird to me and I didn't get it. But then once it just clicked, and after getting over that initial, it's so simple. I was pretty much smooth sailing. Wow, I guess what I'm trying to say is Haskell is great, and if you're interested in programming, you should really learn it, and even if it seems weird at first. Learning Haskell is much like learning to program for the first time. It's fun. It forces you to think differently. It forces you. Wow, that's fun. That sounds like fun because when you force someone, that's fun. Yeah, don't do it like this. Which brings us to the next section. What is Haskell? Haskell is a purely functional programming language. In imperative languages, you get things done by giving the computer a sequence of tasks and then it executes them. While executing them, it can change state. For instance, you set a variable a to 5 and then do some stuff and then set it to something else. You have control flow structures for doing some action several times. In purely functional programming, you don't tell the computer what to do as such, but rather you tell it what stuff is. The factorial of a number is the product of all the numbers from 1 to that number. The sum of a list of numbers is the first number plus the sum of all the other numbers, and so on. You express that in the form of functions. That's me trying to talk like Simon. Like Simon, right? That's his name. Simon. Just Google Simon and Haskell, and you get Simon Haskell. Who is this guy? Simon Baron Haskell. No, the Lord Haskell. No, not the Lord Haskell. Why do I always mix them? Simon PJ. No, Simon PJ Haskell. No, the grandfather of Haskell. Simon Peyton Jones. He's incredible. He is absolutely incredible. I love this guy. He's so nice. He's nice. He's like the Haskell grandfather. He would say, "No, I'm not," and he would say, "There's John Backus, and there's Alonzo Church, and all of these wonderful, purely functional people." Unless you're looking for Haskell nerds, yes, Simon P.J. Glares. For those who not know, Simon P.J. Jones is one of the originators of Haskell. Anyway, where is it? Okay, so this was me trying to talk like him. You also can't set a variable to something and then set it to something else. If you say that a is 5, you can say is something else later because you just said it was 5. What are you, some kind of a liar? Oh yes, it's like if you say a is 5, a is 5, a is 5, right? And if I do a6, a6. What? Yes, this is about scope. I guess I'm not sure how you write. I forgot how you write a binding in Haskell, but kind of like let a is 5 in a, right? And a6. So no, wait. It will be more clear like this. Okay, let's say a is 1, right? And I'll do let a is 2 in a, right? So what's a gonna be? A is gonna be 1. This is about scope. So a was kind of more locally declared with the let statement, and then this a even has no scope. I mean, the scope is like the entire program kind of a thing, right? But if you declare them, well, I'll just stop. Yeah, okay, what are you, some kind of a liar? So in purely functional languages, a function has no side effects. The only thing a function can do is calculate something and return it as a result. At first, this seems kind of limiting, but it actually has some very nice consequences. If a function is called twice with the same parameter, it's guaranteed to return the same result. We want that. That's called referential transparency, and not only does it allow the compiler to reason about the program's behavior, but it also allows you to easily deduce and even prove that a function is correct and then build more complex functions by gluing simple functions together. So, I just want to say, if I start to talk like Simon with a British accent, is because I want to tap into his, wisdom. And by talking like him, I kind of think like him. And then it helps me to understand these complicated things like the double me much better, right? So anyway, try it. Haskell is lazy. That means that unless specifically told otherwise, Haskell won't execute functions and calculate things until it's really forced to show you a result. Laziness, yes, that's great. We love that. I like that because it's a really when you say lazy, it's kind of a negative word, but in functional programming, that's such a positive word. So it's wonderful to change the meaning, to see the word in a different meaning. That's very nice. That's kind of peaceful. That goes well with the referential transparency. It allows you to think of programs as series of transformations on data. All right. It also allows cool things such as infinite data structures. Say you have an immutable list of numbers. X is 1, 2, 3, 4, 5, 6, 7, 8. Wait, okay, X is, let's make a list, 1, 2, 3, 4, 5, 6, 7, 8, right? XH, okay, XH is my list. So, and the function double me, which multiplies every element by 2, and then returns a new list. If we wanted to multiply our list by 8 in an imperative language and did double me, X, it would probably pass through the list once and make a copy and then return it. Then it would pass through the list another 2 times and return the result. In a lazy language, calling double me on a list without forcing it to show you the result ends up in the program sort of telling you, yeah, I'll do it later. But once you want to see the result, the first double me tells the second one, I want the result now. The second one says that to the third one, and the third one reluctantly gives back a double one, which is a 2. The second one receives that and gives back 4 to the first one. The first one sees that and tells you the first element is 8. So it only does one pass through the list, and only when you really need it. That way, when you want something from a lazy language, you can just take some initial data and efficiently transform and mend it so it resembles what you want at the end. Yeah, this was not really clear. No, it is clear, but I think it's very difficult to understand this if you really don't know what's going on. This is like describing someone how something looks like. So even if you, okay, I see you're describing something, but it's hard for me to really see that. So, and we have a list. If I, like, let's define a double me. I think I still remember this. So double me, and this is really cool. With double me, you can, what's a double me, right? A double me is something that takes an argument and doubles it, right? It takes an argument of some type and gives an argument of some type. Well, no, it doubles it. It's one type. So what? Okay, we give it, let's say we get a number, right? And if it doubles it, we should get a 4. So we could do it like x. How do you write it here? Okay, so we do a lambda x and an arrow and an x, right? Interactive error, no instance. You haven't applied a function. All right, so let's apply it. Let's do x, and it's an x, and I'm going to give it a 2. So, okay, so what did I just do? X, x, and a 2. So this is actually an identity function. So an identity function is like, if I give you 2, you give me back a 2. This is a function that does not do anything. Does not, like, it just returns whatever you give it. This is like the most basic Haskell function. This is like the most basic function, is the identity, like, who am I? Who am I? It's not just who am I. You see, this is interesting. This is not about me. This is about some kind of a relation, which comes, yeah, this is great. Like, functional programming is more like about relations than about like what things are. You know, like you of course you can expect a relation, and in the sense, what is a relation, and then inspect it and how it works. But it's more about how things are connected in what ways. And you have all of these wonderful mathematical abstract structures that define not what things are, but how they are interdependent, right? So so if we even give it a string, I think it will work, like apple, and it returns us an apple. So we could give it a name even. We could make an identity is what? Identity is a lambda, or we can just write like this, right? Is a lambda and x. So if we give it it gets an x, it returns an x, and with this slash, we kind of functionalize this thing. So this is a lambda x. Yeah, I don't have it's really important to have the right words, but let me get, so what did he say? Yeah. Wait a second. I was actually quoting this. Functional cafe. Wait a second. Functional cafe. Wait. This is exploration. Notification. Watching C9 lectures. All right. So it's this, right? So look at this. You write an argument, say x, right? So that's this. You write an argument, say x, which is something of type T1. Okay, it's like we don't have types here yet because the identity is there's a word for this, but it includes all the types, right? It's like, I think it's like the biggest class of types, right? Because it gives anything. Like a type could be a type of a number, and if the function takes only a type of a number, you cannot give it a string, because it will say, you just gave me a string and I only accept numbers. So, but anyway, it's still clear. You write an argument, say x, which is something of type T1. Then we write an arrow x, this, right? And then we write an expression of type T2. So that's the expression of type T2 in which we can use x. And then, so we use x here. So yeah, we use x here. And then you write this slash, which is lambda. And then we write this slash. Whenever you write a function, the way you define a value of a function type very closely matches the structure of the types. This slash x is something of type T1, and this expression x is expression of type T2 that can use the value of x. So this is, but this is still static more. We are not doing, we don't have a body of sorts that does something. We just kind of output the result. The result is merely the most simple kind of, like, you almost like don't call it a function, but it is a function. So like, okay, identity x, will this work? It does. So look at this, identity apple. So it gives us an apple. Identity 2, it gives us a 2. Identity, so it can do anything. Can we give it an empty list? It does. It returns us an empty list. But what if we make, so that was the identity. Like we could do a like add function x, xy, and that's x plus y, right? So now we have add and 2 plus 3. So here we have 2 arguments and the body that defines what's he going to do with those 2, 3. So like, isn't this beautiful? Like, look at this. And now look at this lambda. It's so nice. So add 2, 3, 5, right? And you can even like, let's go back to, oh, we need a double me, right? So we were said a double me would be what? Would be an x, and we take an argument, right? An x, and we double it. So we could do x plus x, double me, right? But we could also do x times 2, or we can do x times x, right? So we have a double me now. So now if I do double me 2, we get a 4. And we can even do double me 2, and then we get an 8, because double me 2 is 4 and double me 4 is 8. But since he's only talking here about it, because I don't think this will work on a list, right? Look at this. We have a list, and double me xh. Do you think this is going to work? I don't think so. Right. Why is this not working? Because we have a list. Like, double me works. The definition, the type of a double me is, you see, that's what I miss in Nix-REPL. Double me. So a double me is a function that it's from a num_a class. A num_a class. So from a, I always forget like the exact wording how they describe. I think it's a function from okay, but the class is num, so it's about numbers, and this is take any a is a variable that, so it can take any number. It's a, but any number, right? It's not just a, right? The identity would just have an a, I think, right? That we did. Oh, it's just p and p. All right, but it's like a, so it's p and p, right? So it has no class like that. So it's a num_a, and outputs, this is nice also, a and a. So it takes an argument and it doubles it, right? And this is a type declaration. So how would you, I think you would need to map it. We would have to use a higher order function. So it's like we would have to use a function to apply a function to the double me. So like we have to do something like map double me to this list. Oh yeah, it works. Oh, nice. So right, so this was the list 1, 2, 3, 4, 5, 6, 7, 8, and now we're gonna map our double me. What does this mean? So because double me takes only one argument, as in 2, but if we map the double me, we map it like on the whole list, the mapping on the whole list. So we do map this thing on all list. Mapping is like, all this times everything. Mapping function. We love maps. We love maps. All right. So you could even do like double me h. So would this work? No, this does not work. Double me. Oh, double me h. No, this does not work. All right, let's move on. So Haskell is statically typed. When you compile your program, the compiler knows which piece of code is a number, which is a string, and so on. Am I recording? 25 minutes. All right. That means that a lot of possible errors are caught at compile time. If you try to add together a number and a string, the compiler will whine at you. Haskell uses a very good type system that has a type inference. Yeah, every time when you talk about type inference, use the Simon voice. That means you don't have to explicitly label every piece of code with a type, because the type system can intelligently figure out a lot about it. If you say a is 5 plus 4, you don't have to tell Haskell that a is a number. It can figure that out by itself. Type inference also allows your code to be more general. If a function you make takes 2 parameters and adds them together, and you don't explicitly state their type, the function will work on any 2 parameters that act like numbers. Haskell is elegant and concise because it uses a lot of high-level concepts. Haskell programs are usually shorter than their imperative equivalents, and shorter programs are easier to maintain than longer ones and have less bugs. Well, this is kind of okay. This is like 2 plus 2 is 4. All right. Haskell was made by some really smart folk with PhDs. Yeah. But were they nice? That's important. Were they kind and nice? We hope so. Full work on Haskell began in 1987 when a committee of researchers got together to design a kick-ass language. Simon has a great talk on that. I think it's called Lazy with Class. Lazy with Class, yes. And he talks about how Haskell began and how they met, and he shows a nice photo of it, which is really cool, like Haskell with class. Images, maybe Haskell with class. We find it? No, we just getting a Haskell class attack transport. All right, Haskell class attack transport. I didn't know there was a ship. What's this? This is fiction. U.S. amphibious assault ship. All right, nice. Let's. What you need to dive in. Okay, a text editor and a Haskell compiler. Okay, we have that. GHC can take a Haskell file and compile it, but it also has an interactive mode. Right. Let's come on. Interactive mode is invoked by typing GHCI. We did that. If you have defined some functions in a file called, say, myfunctions.hs, you load up those functions by typing in a colon my functions, colon L my functions. All right, we'll remember that, like load, and then you can play with them provided. And colon R, it's like to reload the current file. All right, so you can change the file, and then when you change the window into GSCI and the file is already loaded, you write reload and it reads the file again that you've changed and saved. There are also much better ways now, like it can, I have to see this now, like it can reload in real time on the side, like you could have it here on the side, and it just reloads the output of whatever you write. Okay, anyway, let's start. Let's start. Look at the baby here. All right, let's get started. If you're the sort of horrible person who doesn't read introductions to things and you skipped it, you might want to read the last section in the introduction anyway, because it explains what you need to follow this tutorial and how we're going to load functions. The first thing we're going to do is run GHC's interactive mode and call some function to get a very basic feel for Haskell. Open your terminal and type in GSCI. We did that. You will be greeted with something like this. All right. Wait, this is updated. 294? Wait a second. 265. Yeah, it must have been updated because this is really old, this book. I remember this book in 2016. In 2016, there was no 2.9.4. So this tutorial is updated. Yeah, I think GCI was like 7 or something back then. Congratulations, you are in GHCI. Here's a simple arithmetic. All right, let's do 2 plus 15. It's 17. Let's do 1 plus 1. Right, so we're just working with values, like directly with values. 3, 2. So that's basically like using a calculator, right? We all know that. This is what makes somehow math, boring because you just, yeah, right? Let's do 49. Let's do 49 times 100, right? Let's do 49 times many zeros. All right. Let's do 34 times lots of zeros. Will it take a long time? No, it did not take a long time. Or it did. Maybe it knows that I just add a 0 and then what would happen if I 34 times 0? Let's just try something. 0, let's see if the same 0, 1. Okay, well, I don't know. 1892 minus 1472. This sounds like very important years. Minus 1472. Is this the year when America was discovered? No, it was way before that. 420. 420. That's like a code. 5 divided by 2, 2.5. 5 divided by 2, 2.5, right? 5 divided by 2, 2.5, right? So in Nix, yeah, if you did this, like 5 divided by 2, you would get a file path. Like you would get like home, username 5. You would get like this. That's because Nix works with file paths. Okay, so this is pretty self-explanatory. Explanatory. It's like outside of. Okay, we can also use several operators on one line, and all the usual precedence rules are obeyed. We can use parentheses to make the precedence explicit or to change it. So now this is okay. It's important when teaching or working, trying to understand Haskell, is to really make this progression from values to functions and to add functionality as you go along. So first we had like values 2 plus 2. So now he's saying he's introducing more operators on one line. So like basically doing 2 plus 2 minus 1, right? So it might, okay, so what's the big deal? But it's introducing 2 operators on one line. And here you can learn about the precedence, right? And how does it, you see, because this is important what we do in math, right? So let's say what the example is 50 times 100, and then it changes the parentheses. Okay, so we have 50 times 100. Oh, he put that in 50 times 100 minus, right? He's doing minus 4999. So that's 1. So that's like 50 times 100, that's 5,000, minus 4,999 is 1. So now, what would be if we do this 100 minus 4,999? Would it be the same? I think it would be the same because the operation of multiplication has a higher precedence than subtraction. Yes, it's still 1, right? But if so, you would have to put it 50 times. You have to put this 100 minus, and now it's different. 9. So now it will first subtract 100. It will subtract 4,999 from 100 times 50, and it will get a different result. We get minus 24,4950, right? So but this is what we know from math, and kind of Haskell respects that. I think there's some kind of little exceptions where you about the function application, because in math you do stuff like this, right? Fx, right? F of x, while in Haskell you don't do that, which is kind of great. Fx is, so the function application is defined by the white space. So if you have fabc, this is same as, so fabc is same as fa, right, and b and c. So it kind of works fa and then b and then c. So it groups on the left and something else groups on the right. Yeah, whatever. Pretty cool. Yeah. Okay. No, it's not, but bear with me. A little pitfall to watch out here is for negating numbers. If we want to have a negative number, it's always best to surround it with parentheses. Doing 5 times minus 1 will make JC yell at you. All right. So yeah, if we do like 5 times minus 3. Yeah, precedence parsing error. Because, okay, we have to group it like 5 times and minus 3. So then it works. Okay, that kind of makes sense, even, you know, visually. Boolean, I bent to the Boolean grade type, whatever. Boolean algebra is also pretty straightforward. As you probably know, this is the Boolean operator AND, right? Means a Boolean AND this means or not negates a true or a false. So true and false is false. True, so true and false is false. True and true is true. False and false is false. And false and true is false. So we have a lot of falses. Yeah, this will later come in handy when we do guards. This is kind of cool. Or pattern matching. Yeah, pattern matching, because you see only true and true gives true. True and false gives false. False and false gives false. And false and true gives false. So basically, we wouldn't have to define it like all 4 times. You could just say true and true will give true. But there are also better ways, and everything else is false, you know, stuff like that. We have false or true. Oh, we have false or true. False or true is true. False or true is true, right? And false or false is false, right? So not false. We have a not false, not false. So not is actually not, I think not in some sense is a step up a bit from false and true, because not says something about the value itself of something provided. Not sure. So not true and true, not false. Yeah, you can like not false, not false, but you can mix. So not true and true. So true and true is true, but not true is false. Okay, so that's false. So that's kind of cool. It would be nice to build some things with true and false. Yeah, there are these binary, what are they named? Not false, not or. That's like the basics of also computation in some sense, but it's more about how the process, those gates, what are they called? Gates, logic gates, true, false, false, true, and or not. Yeah, let's just move on, right? Testing for equality is done like so. 5, this is the equality, 5, 5. I like how these the equality sign, it connects. It's kind of nice. 5 and 5 is true. 5 and 6 is false. Would it be like 5 minus 2 is same as 6 minus 3? True, yeah. It does a calculation. So true is equal to true. True. So false and true is false. Let's do false and false is equal to true and false. You see, false, this is interesting. False and false is false, right? And true and false, false is false. So if we compare those two, is false and false. You see, this is like how the mind works. I was almost expecting it will write true. Like, is this the same as this? It's not the same. Is false, let's try, is false same as false? True. All right, is false and false the same as false and false? It's false. I didn't know this. So false is same as false, and false is same as false and false. But shouldn't this be the same? Yeah, this is interesting. 1 is 1. This is testing for equality. 5 is not the same. True. What is this? Oh, this is equality. This is not equal. So this, you can compare strings like hello and world. No, this will not be the same. So probably we have to use like this. Yeah, hello world. This will be true. And hello. Oh, this is true, right? All right, let's move on. What about doing 5 plus llama or 5 is true? Well, if we try the first snippet, we get a big scary error message. Of course, you can't add a string to a string. No instance for num string arising from the literal 5. Yes. In the first argument of plus, namely 5, in the expression 5 plus string, in an equation for it, 5 plus string, you can add a number to a string. Like you wouldn't know even in real life what to do with it, right? You can't even do 5 plus 6, right? Can't do that. You could change 6 to a number with a function. Like there's probably something like 2num, from string to num. You apply that to the 6 string and then 5 plus that. You could do that. But yeah. And 5 is equal to true? No, big 5 is equal to 5, not to true, right? You can't compare a Boolean with a number. No instance, right? What GACI is telling us is their llama is not a number, and so it doesn't know how to add it to 5, even if it wasn't llama, but at 4, Haskell still wouldn't consider it to be a number. Plus expects its left and right side to be numbers. If we try to do true equals 5, GACI would tell us that the types don't match, whereas plus works only on things that are considered numbers. Equality works on any two things that can be compared, but the catch is that they both have to be the same type of thing. you can't compare apples and oranges. We'll take a closer look at the types a bit later. Note, you can do 5 plus 4.0 because 5 is sneaky and can act like an integer or a floating point number. 4.0 can't act like an integer, so 5 is the one that has to adapt. Oh, 5 plus 0. So 5 will adapt to a floating point, right? Okay. You may not have known, but we've been using functions now all along. For instance, multiplication is a function that takes two numbers and multiplies them. As you've seen, we call it by sandwiching it between them. This is what we call an infix function. Yeah, this is an infix function. Most functions that aren't used with numbers are prefix functions. Let's take a look at them. Functions are usually prefix. So from now on, we won't explicitly state that a function is of the prefix form, we'll just assume it. In most imperative languages, functions are called by writing the function name and then writing its parameters in parentheses, usually separated by commas. In Haskell, functions are called by writing the function name, a space, and then the parameters separated by spaces. For a start, we'll try calling one of the most boring functions in Haskell, succ. Successor. So the successor takes anything that has a defined successor and returns that successor. What? As you can see, we just separate the function name from the parameter with a space. Calling a function with several parameters is also simple. The functions min and max take two things that can be put in order. Min returns the one that's lesser and max returns the one that's greater. Successor. I like, so succ 8, 9. But successor, so maybe that's the most proper. I remember the increment. And that's from the yeah, we need this music. I really want in every episode to start like this. Do I have enabled desktop audio? Yeah, I have. Oh, just a second. All right, so I'll have to stop now, and for the end I want to play this incredible music from Science, Structure and Interpretation of Computer Programs, one of the most legendary things ever made.
I'd like to welcome you to this course on computer science.
No, it's not about computer science.
Actually, that's a terrible way to start. Computer science is a terrible name for this business. First of all, it's not a science. It might be engineering, or it might be art, or we'll actually see that computer, so-called science, actually has a lot in common with magic. And we'll see that in this course. So it's not a science. It's also not really very much about computers.
It's not about computers, right?
And it's not about computers in the same sense that physics is not really about particle accelerators. And biology is not really about microscopes and petri dishes. And it's not about computers in the same sense that geometry is not really about using.
All right, I will have to end, but this is a wonderful lecture, and it's true, especially with Haskell. Like, you can do it in your head, which is hard, or in your paper. Okay, that's it for now. We've stopped at the successor, so we'll just continue from the successor next time. I have to go. I really like this, the vibe of this, and I'm gonna be making this until the end, right? This is so exciting. All right, learn new a Haskell for greater good.